This is the life. Oh. Hey guys. Welcome. Welcome to Conservation of Energy. You're probably wondering why I'm sitting here relaxed, reclining, taking it easy. And the reason is because we've just shifted into a new gear here in the physics department. So you just did a month and a half of studying motion, changes in motion, and the causes of changes in motion. And that's pretty much it. We're done with physics. You guys can go home. I'm just messing with you on that one. But what we are now looking at is conservation of energy. And instead of creating new ideas, we're going to workshop ideas based off of things that we observe. So before we get into that, let's take a look at this week's PreLab activity. So in today's PreLab activity, what we're looking at is a simulation that will allow us to visualize in an ideal situation conservation of energy. So let's dive in. We have here the energy skate park. And the first place we want to go is the graphs. After you've taken a look at the controls palette, so double click on that. Look at the controls palette over here and look at everything that's here in the PreLab guide. Come back over here and take a look. We're going to turn the speed on. So the speedometer is going over here. And then we're going to, you've got your friction. We're going to leave that off so you can go immediately turn off thermal energy. That's again kind of the friction does this transferring mechanical energy to heat. Gravity can change to Jupiter. Who doesn't want to try and figure out what gravity is like on Jupiter? But it's worth taking a look at that. You can have a little bit of fun with that. So I'll let you guys explore that. With mass here, we're not going to change anything in that regard. You can change your avatar to be more representative if you like. So if you do feel a little bit like a cat or a dog or, somebody with unkempt hair, that's perfectly an option. And so I'm going to set my skater up here on top. She's going to start immediately, start falling. And note this is on position, your energy as a function of position. Now let's take a look at the energy as a function of time. And we're going to let this run for the full 10 seconds. And what you'll want to pay attention to is just how the kinetic energy, potential energy continue to go back and forth between each other. So we're going to pause this here. And this is your opportunity now to go ahead and answer the questions here at the top of the worksheet. So now that you've completed that, then the PreLab says, so let's go over to the intro here and get started. Once again, you can fiddle with the settings here just to kind of have a general sense of effects before you take the actual data, because it's interesting to start her motion and pause it midway and change the gravity to higher or lower and see that has effect, or change the mass. That's probably a little more instructive, but for comic purposes, worth taking a look at changing the gravity mid-motion. Anyways, and you can also change the track shape if you like, but we're not going to worry about that. We'll place her on the let her begin going, and note the exchange, the back and forth. This is now a little bit more familiar after doing the first part, and we're going to pause it as we get close to the top, not completely the top. And the idea is, look at your graph here. You're going to sketch this graph on your paper, but take care to recognize that if we draw a straight line here, as I'm demonstrating, this is not the potential energy is not the same height as the total energy, and the gap that's different should be equivalent to the kinetic energy. And then you draw it when she gets close to the bottom. Let's see if we can get that. There we go. It doesn't have to be exactly on the bottom, exactly at the top, just enough to see some difference there. And again, your line that goes across here leaves a gap that's about the same height as your potential there. So something interesting to keep in mind as you answer your questions as you're doing for the second part of the submit sheet. And then that's pretty much it. There's no need for a screenshot on this one. I just want you to play with it a little bit for a few minutes before you make your recordings and think about how the things that you change, the gravity, so mgh, and the mass, so both potential and kinetic energy have a mass factor in there that will allow us to proceed from there. So, okay. Okay, so we've talked about motion, we've talked about forces causing changes in motion, and we talked about,
Okay, that's more like it. Okay, so as I was saying, we were talking about kinematics. We've talked about forces that cause the changes in motion. Now we want to see what else can we glean from just simply looking at things motions. So let's take a closer look at a force acting on an object, the before and the after state of that. Bum, 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 bum. All right, here we have a track. I'm going to push on this this cart, this little cart on this air track, and when I give it a push, I'm going to give it a push. So here I have this cart sitting on this track, and I can give it a push and a nudge. We can do Newton's first law and second law the way that we did it before, but now we're going to see what happens when we really kind of dissect the changes in motion. So if I start this guy here and I give it a push, you can see it slows to a stop right away. So what I'm going to do now is I'm going to turn on the air and see if we get a different response. If I push it, and now I take my finger off, and you can see it's now in motion. It was at rest, and now it's in motion. Let's do that one more time. So I'm adding a force to it, and now its motion is different. Very clearly a different motion. What is happening? So the question now becomes, when I applied the force to it, what changed about the cart once I took the force off that kept it in motion? So the most important thing that stands out about that is we have a before state, and an after state where the object was at rest and then it was in motion. And so that force caused that to happen, and it did so over a displacement. So here you have behind me definition of work. We're going to just call this thing work. Work does something. We're just going to call it work for now, but think about what that means as it goes along. Something we're calling work is a force applied times a displacement. You'll notice that this definition here has this special dot right here, which is what we refer to as the inner product or the scalar product. And if you jump to the end of this video, you'll see that I've got a little segment that talks about the mathematics behind that, just so you can see what's going on there. But these are two vectors that are multiplying to each other in this special way, and the result of this multiplication, this product of two vectors, is actually a scalar. So you get two vectors, you get out a scalar. Anyways, so we have this definition that we're just going to call work for now. We do some work. We moved that object, we moved that cart across the track just by applying a force. It traveled some distance, and it did change motion in the course of that action. So we're going to call that work that we did on the cart. We say, well, what's the force that we did? Well, the force that we acted on is mass times acceleration, Newton's second law. We're just throwing that in that place, and delta x. And we say, does that anything look familiar here? So maybe it looks familiar. So we go back to our kinematic equations. We've got this resource available to us. We say, wait a second, we have that one that we don't use too often because it doesn't have time in it. Velocity squared at some point is equal to the initial velocity squared plus 2 times acceleration times displacement. We say, well, there's a delta x right there, so let's solve for that and see what we get. Do that process. As you can see, these are familiar algebra processes, and we have a delta x is equal to a phrase over here, velocities and a 1/2 in there. So let's stick that back in there, and there it is. Now we have work is equal to mass times this business. Let's distribute that. Now we have a statement that says work is 1/2 mv squared minus 1/2 v naught squared times mass. And we say, well, what do we do with that? Well, work is something that we do to something. We think about work in this vernacular thing where, oh, I did a lot of work today. That's probably true, but that's more like, biological exertion work, not the same as physics work, which is specifically force causing a displacement. So looking at this, we say, well, what does this mean? This is motion. This is an object that's in motion. This is an object that had different motion. Let's define this as energy of motion. So we're going to call this kinetic energy. And that kinetic energy is defined as 1/2 mass times the velocity squared. We plug that into this expression. Now we can define work as final minus initial kinetic energy. Therefore, we call that
the change in kinetic energy, or this is your work energy theorem. Okay, so that gives us a little bit of insight as far as things that are in motion, but what about things that are in a particular point in position in space? For example, here's a tennis ball. And one thing I like to demonstrate is Newton's first law, and our tennis ball just sitting on the tabletop. And one thing that we've talked about in those demos is there it is, not falling. And if I remove this, then it can move, and there's energy of motion transferred to the ball. So we need to answer the question about where's that energy coming from? How is it collecting that energy from gravity? So here's our tennis ball. Up here, it's got some initial height. It's got a final height after it's been falling for some time frame, and it's under the influence of gravity only. And so we take the definition, work. Work is, in this case, a force, gravitational force, acting on the displacement. It's in the y direction, so let's change our variables to fit that. And we put m. The acceleration is negative g because we're defining this as positive up in this case. Final minus initial positions, and then we distribute everything, keep that minus sign on the outside here so we can still see final minus initial on the inside. And we go, okay, mgy final, mgy initial. Let's now define gravitational potential energy, where we say PE, gravity, is equal to mass times gravity times the position in space. Sometimes you may see this as h, height. This is our definition of gravitational potential energy, and we plug this into place. We have a definition now for work that is negative gravitational potential energy final minus initial, or the negative change in potential energy. So work done on this object to fall will take energy away from the potential and transfer it to the positive change in kinetic energy. So now we have a definition for kinetic energy, energy of motion. We have a definition for potential energy, the energy of position gravitationally relative to the center of the Earth. And so for an object that's moving in space, it's going to, at every point, have some height and some kinetic energy. And we can put those together and describe its total energy at that point in space, and time, part of its motion, what have you. So let's do that. We put those together. We call that the total mechanical energy. And it's exactly what we say. It's the kinetic energy at that point, 1/2 mv squared, and the gravitational potential energy, mgy. You may see it sometimes mgh, depending on the user who's talking about it. This is the total energy of the system. So going back to our example with the cart and the track, we can now think about the fact that in the process of applying a force to cause the displacement, we are transferring kinetic energy to it. And since it's on a level track in that case, the potential energy doesn't change. So we're transferring kinetic energy exclusively to the track. Keep in mind that some forces don't act on an object, they react to an object in motion, namely friction is a good example. Wind resistance is basically air friction. Water resistance, the same. But if for some reason we have an ideal situation where energy is not lost, or at least not appreciably lost, then we can consider the total energy before and the total energy after some period of time within that motion, initial, final points of interest. Then the kinetic energy, potential energy at those states can be explained. And if we rearrange this to get all potential energy on one side, the kinetic energy on the other side, then we have a negative change in potential energy is equal to the total change in kinetic energy. That feels very explanatory. It says, okay, well, the energy can be somewhere. It's either going to be in gravitational potential energy, or it's going to be in the kinetic energy of an object, such as pendulum is a good example. But if we shift this over to the same side, then we can make the statement that the total change in potential energy and the total change in kinetic energy sums to zero in a situation where energy is not lost, and this is our conservation of mechanical energy. Okay, so we've launched the Pasco Capstone software, just as we normally do. We'll click on Hardware Setup over here on the left. I'm going to click on the first channel. Of course, you can always put it on any one of those channels, but click on the channel. And although we're using a photo gate, we want to use the picket fence because we want it to take multiple start and stop triggers. So we click on picket fence. You can click on timer setup. Mostly you're just going to confirm that everything is in place. Photo gate, picket fence flag spacing is 0.05 meters or 5 centimeters. The specifier's name is, the timer's name is picket fence, so that's all good, and you can close the timer setup. We want to take a look at the graph. So we'll grab and drag a graph over here, and I want to shrink that up. So this is to make some space because I want to have the table out here as well. We're going to need more table space there. We'll click on the select measurement. We want this to be speed versus time. It'll automatically populate speed versus time. And then you've got your table here, so we'll put time times. And then we'll add another one. Use this button over here in the upper left, the insert columns. And we'll click on this, and this one will give us position. Once this is set up, you can go ahead and take data in the normal way. So here we have the setup that's going to be a slight variation from lab 1. In this case, you can see that you have more control over the release and control so that it falls a little bit more cleanly. You have your box down below that you can't see but believe it's there. And then we've got the ability here to measure the distance between the reference point, probably the base, could be the table, but could be the base of the mount. And you want to measure the distance to the beam line that you'll be breaking and the distance to the actual bottom band that you have. Now you can adjust this, and I encourage everybody in the group to adjust this by just giving this a little adjustment like so. Move it up and down. You can go as high as you like, as low as you like. It's a less interesting result to have it too close to that, so you want to have it a few centimeters minimum from that point. And then once you are satisfied that you have your measurements and recorded, measurements recorded here, measurements recorded to your bottommost band. And the reason that you want to take that measurement of that distance is because you're going to use the conservation of energy to predict where that dropped from the bottommost band, how far it fell, and compare that to the measured distance, difference of those measured distances that you just took. Then you'll start the data. Give it a second. There's no need to rush and try and synchronize these things, so you can just go ahead and give it a second to begin data collection, and then give it another beat or so, and then make sure that you're careful about the placement. This is going to let it fall. You can see it's got a little bit of a tilt already. Close to the center as you can get. And it will wobble a little bit, but once you let go of it, it's just going to fall. But you so we'll stop. We'll stop, and what we'll do now is we'll zoom in on the spot. So we go over here to the scale axes button. It'll fill in the space. You can highlight all the data. It should be a nice straight line, and we'll come out. We got 9.76, which just a quick calculator run with percent error. So we'll do 9. And that's 0.47, 0.48% error. So this is a good data. This is good data to use. So we don't have to take any more data for me. Remember, multiple partners, you want to have your own data individually. Click on data summary. We're going to go in here and tell it to, tell it to give us new numerical format. Get it up to 6 decimal places. And the reason we go up to 6 is once you increase it to 7, you just start adding zeros. We've reached the limit of what the system is able to account for. I'm going to save this data. Now I can export the data. So we're going to click on export. Remember, if you try to export before you save, you risk the system crashing and your data disappearing. This is not a long lab, but it's still frustrating to have to redo. You can export all this information, but we really don't need block event times or block-to-block times for our analysis. We just want to have a record of it in case we need to go back and review it without having to rerun the data. So it's saved in Capstone, and we're going to go ahead and turn off acceleration, and we'll make sure that block event times will be turned off. So all we're getting is time, speed, and position. And we'll check the export format. We want that to go out as comma separated value, a CSV file. That's the one that's going to automatically look like Excel. We just have to resave it as an Excel file at the time. So we export to file. We go into where we want to have our information, and we hit save. And we close that. We've done what we need to do in Capstone. So let's head over to Excel and do the analysis. Okay, so now that you've taken your data drop, your single one drop, we don't need to do all the same stuff we did last time. One time will do the trick. And this is what you see. You've got times that are indicated in the first column. You got your block events and your block to block events. And you'll notice that they occupy different timestamps. And you have your speed that is computed by the system. And you have a position that is also determined by the bands of the picket fence as they fall through the photo gate and break the infrared beam. And so, as always, this is the CSV file. So it's quickly file, save as, and I always like to keep it local on my device. I'm old-fashioned that way, you might say. And I'm going to change that to the... And I'm going to click on this to change this to a workbook, just as usual. And then hit save. And now it's a workbook as usual. And once again, it's very important. As scientists, we don't want to disrupt data or destroy data, get rid of it altogether. We want to keep the data because there may be a reason sometime in the future to go back to that data that you didn't have an initial reason for, but now you have that data captured. It is very valuable. Even if it ultimately turns out to be not useful, it's valuable because it is an instance when you had control over a situation and you made a measurement. So that's the important reason to keep any data that you keep. We'll add on a new guy, and I'm just going to copy and paste this whole bit of data over here, so you can do it any number of ways. Go over to the sheet, Control V, and this one is going to be my energy analysis. Okay. What's the most important thing here is the speed and the position, but we need to get them on the same track because they're currently at different timestamps. So here's what we're going to do. Now, what I'm going to do now is walk through a more avant-garde, a little bit more loose approach to doing the stuff in Excel, because what I want you to do at this point in time is start to learn to branch out in your own style of data management and thinking about what do we want to have in our lab report, because this is a short lab report, so we got to be thinking about that. Well, one thing I know that I need, for one, is that when I drop this, I had this at different heights, or at a particular height. So I need to have a space for heights. And so I'll put this right here as, let's say, beam height. Beam height, and then I'll have band height. That's going to be the bottommost band on the picket fence. And then I'm going to come over here and put this in, first in what we saw was centimeters, and then meters. Why in both of those cases? Because of the fact that we can put formulas into Excel and let Excel do the hard lifting of making sure our decimals are in the right place, the formatting is in the right place before we copy and paste this over into Word and further make any adjustments that need to happen there. So in this case, my height was 5.3 centimeters for the beam height, and then I had 11.2 centimeters for the 11 centimeters and 2 millimeters for that. And then what I like to do is I like to highlight with the cells with a gray to let me know I've got a formula there, and I'll put equals this number divided by, these are in centimeters to meters, that's not 1,000, that's a factor of 100, so divide by 100, and then you can just click and drag. You can copy and paste. Either one of those will copy the cells just fine. And as a result, I need to know the distance between those two, so I'm going to put the y underscore init, and this will be what initial height, and I'll worry about the formatting in Word. I'll make sure to change this formatting so it's a y with a subscript, initial position, comma, measured. Okay, so I'm going to put measure there in the case. And that's going to be a simple calculation also, equals this minus this guy right here. Enter. And of course we can, and this is also a calculation, so I'll make that gray as well. So this is good to go for heights. And I can even put a frame around it and have it ready to go for copy to paste. You don't have to do it this way. You can flip-flop the arrangement. You can make it a stack. You can arrange it in a way that you feel helps tell your story. We also have a mass of the picket fence because you measure it in grams and then have it converted to kilograms. Really, that's the other reason to do tables the way that I show you guys, is because you want to show what measurement you made the scale in, and then convert it to the functional scale, the usable scale that you do for any operations or something. So in this case, my case was 41.5 grams, and then this will be, again, equals divided by 1,000 in this case, and hit a grade to make that calculation. Good. Next, we want kinetic energy analysis. And what do we do there? Well, I'm going to need time to put that here. And I'm going to need the speed because kinetic energy uses 1/2 mv squared. So I'm going to put that here like so. And I'm going to create a, what do we want the kinetic energy? And that's going to be in joules. I'm going to leave this one blank. I'm not going to reorganize these because I can. And when I go to do this later, I will simplify this. But for now, for me to keep track of where everything is and make the least amount of change to the data, because I can just copy and paste as data, as values later on, and then sort from there. But right now I'm dealing with functions and variables in Excel. I'm using it as an active thinking process. So having everything in particular places, leaving the data unchanged, reduces the risk that I move something poorly. So we'll do the rearrangements right before I copy and paste this into Word. And in this case, I'm going to do 1/2, so I'm going to use 0.5 in this case, times mass. So I can just go over here to the mass I've got in kilograms, times, and then I need the velocity squared, so that's the speed squared, this raised to the squared. A similar way to do this is if I come up into this, and let's call it like a safer way to put it, is put this in parentheses so that squared, you don't feel like maybe it's going to read the order of operations wrong. So we put that inside the parentheses. Then when it does the order of operations, it'll do the parentheses, it'll do speed squared times the mass times the 1/2. Enter. Make sure you don't have a typo. One thing that I should point out is that, watch what I do here. I'm going to click on this to shorten the decimal places, and I just want to make a demonstration. When I show expand it out, it does some rounding sometimes, especially if it's above 5 for the number that we're rounding past. But it doesn't change the value that's in the cell as far as the memory is concerned. It just changes what it shows you. What we put into Excel, or what you display on Word, is going to be the actual value that you are displaying. That's going to be what's in the cell. So it's important to be aware that it's not changing the value. It's not actually rounding the value. It's displaying the rounded value. So, and then I'll grab the two of these, because if I just grab this and copy down, then you see that there's a problem. But the other thing that you notice is that they're all zeros. Well, that's because if I click in here and highlight the cells, remember how Excel works. It grabs the cell relative to the current cell's location if you go click on that cell, which is fine in most cases. But in this case, we're copying and pasting formula that is changing positions in cells. So it's going to direct to progressively further down cells over here along this column J. So we need to tell it to stay with this particular cell J9. So I'm going to come up here and here. I'm going to change this to a $sign. So we'll go up to the original. So I'm going to go up to the original formula, and where it says J9, put a $sign before the J that says go focus directly to column J, and then go directly to row 9 and stay with that function. Don't let this one change as you go throughout. I want that absolute location on the spreadsheet, not the relative to my current cell for this particular value is going to capture. Do that. Nothing changes there. Also, I don't want these formulas here in this gap here. So I'm going to capture both of these, and I'm going to copy and paste this pattern, empty and formula, and go all the way down. Now you've got a much clearer looking graph, and when we copy and paste this into another spot and use the sort function, it'll be uh, it'll be a nicer thing to do because we won't have those gaps, because we'll be able to eliminate those gaps using the sort function and not worry about extra zeros and whatever that may show up. So this is our kinetic energy, and I'm going to highlight this one with I guess blue, since that's what we saw in there. I like colors. This is what works for me. There's, some of you don't use colors, and that's fine. But this is the kinetic energy, and that helps me to keep track of what's going on. We're going to go ahead and create a potential energy analysis. We're going to have to do a little extra thinking on this one because of the fact that they're out of alignment. So, come capture the same time scale. Control copy. I'm using arrow over and then a shift and hold down to do that. A lot of tips and tricks that we can learn from Excel. And most of these tips and tricks do translate to other areas if you're more interested to, separately to do Google Docs and Sheets and what have you. Mind you that if you have a MacBook, there may be some truncated functionality in some of these, but mostly it's just a limited keyboard and a couple of things that are different in how they want the website, the app to operate. Copy, come over here, set right next to here, paste. And here's the trick now. These are the absolute position where it knows 0 is that band, that first band, and so every successive band is 5 centimeters away. But that's not where the kinetic energy is placed. As a matter of fact, what's happening with the kinetic energy is it says, okay, I've got this timestamp here. Remember, it's distance divided by time equals final minus initial divided by delta t. And you can see that calculated the speed at the time that's halfway between those two. Equals this minus this. If I copy and paste that here, you can see that this one is going to take the difference between these two values. And so this is just giving the velocity of the halfway point as a single object as if it was falling. And so that's why what's going on here is what we're doing. So I'm going to delete those, get those out of the way. In other words, what we need to do is have the position of this timestamp that where the velocity is being marked from. So we can do that within, just take the average of those two values. But the catch there is that, remember, this is going downward, and so we need the successive displacements to be where the bottom is relative to the band that's making that marking. So we need to make it a minus sign, equals minus average of this, and I'll use a comma in this case, so don't use a other value. And then I can repeat the trick I did before to copy and paste these down, and you can see it fills it in as such. And these are going to be called midpoint displacement. So these are called midpoint displacement. And again, that's in meters. And so this part is ready to go. And then finally, we need the potential energy for these locations. So potential energy, and again, that's in joules. And we say equals mass. So we'll do, again, J9. I'll go ahead and just type it in there. We got equals $J $9 times the gravity, and this time we're 9.80665 times the y position, height, and close that, enter. Copy that down as we did. This one I'll make, I think it was green. And the other one, potential energy. And it seems like, okay, we see some stuff here. But let's do total energy analysis. Total energy. If we assume that all the energy of the motion being the parts that relative to its position, aka it's instantaneous at rest, and its kinetic energy, the energy of instantaneous motion at that point. We're going to add those two up, and we get, well, there's nothing here. So let's go down here. Equals this plus this. Enter. And then I can copy and paste this down like so. And so you can see these numbers look fairly in agreement with each other. As a matter of fact, if you want to, you can come back over here and just look at your, let's do a quick insert just to see, because you've seen this data before. This is not new data. This is new data, but it's not a new process. And I'm going to turn off, select data, turn off the time details, and just get the speed, and you're going to see what we did in lab 1. Quick layout. I'm going to take the 9th option on there to get that preset in there, and let's delete those silly extra minor grid lines. 9.763, and you can see this is kind of what you would see if we were looking at this as a lab 1 item. But, and what I'm noticing here is that these are a little bit a kilter a bit, but that means ever so slightly. Let's do an average. Equals average, open parentheses, and then go shift up arrow, and then enter. It'll automatically populate the closed parentheses in that case. And you got 0.224. What about percent error or percent difference? Do we want to use percent error or percent difference in this one? It's at this point you want to be recognizing that percent error really requires us to have something that we can agree upon is the point. But we just kind of dropped this, and we could use whatever the total energy that it has at that point as the reference point, but we're not sure. So let's do difference in this case. And remember, I put parentheses percent as the thing. So instead of percent difference, it's the difference by units of percentage. So it's again expressing what we're looking at and how we're looking at, aka what units we're using. Equals, now we're going to have to use a lot of those dollar signs in this case. So we're going to take the difference between our measured value for an individual run minus our reference point down here. That's W18. We go up to the top, click on dollar sign, click on dollar sign, close, divide by, and you can type all that other stuff, or we can just take the average, which the denominator is for that, and we'll take this guy, comma, and we'll just dollar sign W, dollar sign 18, and then close that. And you can see there's that. Immediately take the opportunity to go ahead and truncate your decimal places. We don't need all those decimal places. Go ahead and truncate those, and then let's grab and drag this down like so. And you can see good data pretty much all the way across. And now you ask yourself, okay, let me take a quick look at my picket fence itself and see if we can figure out what may be causing these big jumps here that don't stand with the rest of the crew. That can give us, again, further information about how well our experimental setup contribute to individual data points and to the results. Okay, so you'll want to combine all these into the same point. This is what I was talking about earlier here. I'm going to go ahead and copy this. So what I'll do is I'll create a new sheet, and this one I'm going to label tables for short line report, for example. And this will be one, so I'll copy this one, Control C or Command C if you're a Macer. And right click, we're going to paste special just the values. You see it doesn't bring over the frame, so you can go and add that frame now. Then you come over here and say, all right, what about all this business? So I'm going to just highlight these, copy, come over here, tables for short lab report, and this will be my energy analysis data. You're going to graph this, but you want them all together at the same time to see the percent difference, percent error. So now I've got this pasted in here. Do we need to keep all this data? It's another question you should always be asking yourself. Do we need to keep this data? What benefit does it serve to telling the story? In this case, the speed, I don't need to see the speed because the speed is used as a secondary, it's an intermediate step towards calculating the energy. So I'm going to delete that from here. I'm not changing anything. It's still here. But for my tables, I also don't need the time again because I've already got the time. Same thing for position and midpoint position. We don't need to see those. Those are calculations. There are things that you can discuss about what you did in the body text without showing it as part of your graph or your tables, because the tables need to be that pertinent information. Can you demonstrate what you need to demonstrate with the least amount of redundancy? So you want to have redundancy, but not too much. So here we have everything. So if I copy, move that over, paste. Let's move all this over, Control X, paste, and then I'm going to move these guys over, X and paste. All right, now copying this, go to Data. The pop-up is not going to be shown, but you're going to click on the sort by column H, let's say. In this case, it doesn't matter because we're going to change back to using time. And I can delete these. Remember, I pasted all this in as values, so these are all values. I'm not changing any results. But then I just go here, and it should keep it the same because the way they increased. No headers. And I'm going to change it. I'm going to increase it by time, so as time progresses. No change, no significant change here. Look at all these decimal places here. We got to clean this up for the worksheet. So let's put a frame around it. And with the time, you can probably truncate the time. You can report in there that you had 7 decimal places of precision, kinetic energy, potential energy. Truncate that down to a few decimal places, and then total energy should have the same. I'm thinking 3 or 4 decimal places in this case. Yes, there are sig figs. Here's let's say a truth of the matter. We did not measure the actual distance between the bands. We take them as 5, and that it's exactly 5 centimeters. So it's been a presumption for any work that we've done with these picket fences that we know the precision. Remember, the precision is how many decimal places we know, how well we know the distance or the length for a measurement in regards to making that measurement. So strictly speaking, we only actually have 1 decimal place, 1 sig fig, if we were going to use that for, if we were going to use that for our guideposts. These are derived data points, and so there's ways to propagate significant figures. In this case, we'd only keep 1 decimal place because of that. But in this case, we're going to fudge that factor, assume that we know that indefinitely precisely, and use that in this case to choose a sig fig or a number of decimal places. That makes this nice to look at. You can, in other words, you can fuss about sig figs another time. So finally, the percent difference, we're going to truncate this, boom, 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 get that down to 2 decimal places. And you can even, now these are all over 1. You can do this number right here and see the entire stuff. But keep in mind, you could change this and make this, instead of kinetic energy, it's now KE, time sub number 2, delete. You don't even need to have number 2, you can just have time, and that should be lowercase t anyways. And so on. I'm not going to belabor the point, but you can do that, and difference can be shortened to just diff. I put diff period just to be a little professional on that regard. Be careful about the alignment here. These in Excel, strings default to the left alignment, numbers, calculations, formulas, values, true numerical values default to the right. So you're going to want to align these all center, all left, all right, whatever you want to do so that you can have that. I always like to default to center myself, but go with what your preference is. Okay, this is, I want you to be developing your own style of presentation of your material. And then finally, you need to have a table that shows your height, your experimental height. How high did it go? And so we say, all right, let's see here. So we need the total energy. That's this guy right here, and the initial height, y underscore init underscore experimental. That's going to be through the process, and there's units to go with that. I'm not going to belabor right here. Remember, gotta build your own style. Equals, we're going to have the total energy at the beginning, right before you dropped it, there was a total amount of energy. It's this 0.0224 on the value. And so we need that total energy is going to be equal to the potential energy at that point. Well, if we take the total energy, this guy, and divide it by parentheses, the mass times 9.80665, and close that parentheses, we'll get a height of 0.055. This is in meters. So this one right here, you'll compare to this value up here, the initial measured. And you can do that by percent, again, percent difference, and show 100 times, open parentheses, the experimental value minus what you measured, divided by average of those two values. One thing to note, we don't need the dollar signs when we do this part because we're not copying and pasting to, we're not going to be propagating this formula, making a one-time calculation. And, oop, that doesn't seem right. That's because I use the grams. So this makes that's a K. I'll make this a K. We want the kilograms to or meters to meters, and now it's 0.69%. You say, well, what do you think contributed to getting this wrong? Or what do you think contributed to this percent error being greater than 5%? And I think the answer will come pretty clearly for you as you consider this, but it's worth commenting on. So keep in mind that when you put these objects into Excel, and making the graph is pretty straightforward as well, so I'm going to leave that to you to do. But so you can put your caption here, for example. Let's make this a single one, and we can type table 1. Initial condition measurements, and you can include your mass in there. When you copy and paste this into Word, it'll come in there in the format and be much nicer, but you should be good to go with that. Okay, I don't know that I might keep that. Probably going to tell us that, but that's good. There you go. All right. Oh yeah. So remember, whenever you put an object into your Word for your short lab report, put a caption on it. Make sure that it looks decently nice. So you don't have to fill up the entire page. You can resize it to be a little bit nicer and a little bit more manageable. But put your caption in place. Then go to the body text and say, we added this, we did this data, and we examined it with yada, yada, yada. And you can see that in table 1, figure 1, etc. Then you add a sentence that says, note that this stands out about that. That's the best way to start populating and filling in that section of your short lab report. Well, I guess that's everything for this week's lab. So make sure if you have any questions on your lab report that you talk to your TA, talk to me, talk to your classmates, and let's build this knowledge together. And until then, we'll see you in the lab. Take it easy, guys. Bye. Here I have a track. And isn't it attractive? All right, let's see. Bing. I do my own sound effects, folks. I get paid extra for it. All right, so Now we move on to the next one because I already read it.
You can't hear me right now, but what I'm basically doing is I'm pushing on. If you can hear this, you update here.
Easy peasy. Lemon squeezy. There are going to be bloopers, guys. Tennis ball, where are you, tennis ball? My physics tennis ball. Tennis ball, my physics tennis ball. Here we have a track, and in this track, it is distracting. But-a-bumps. All right. Thank you here. I'm here all week. Yeah. All right, let's see here. What else am I thinking here? Track cart. So here I have this track on this cart. Maybe it's the other way around. Cuts to that. We'll do a little dance while I'm waiting for the cut to be done. Okay, the cut's finished. This idea.
Just start over from the beginning because I made spattery noises. Now I'll shut up and sit down.
So now that we have definitions for concept.
So let's take a quick look at the mathematics that are underlying the multiplication of the vectors force times delta x in order to give us back a scalar. So in this case, want to keep in mind the fundamental idea here is we have two vectors that are happening, a force going this direction and a displacement going this direction, as we saw, for example, with the track. And so we need a definition where the vector quantity will go away, but the scalar quantity will be retained, and it's due to the fact they're going the same direction. For example, if we're pushing the cart along, we didn't add any gravitational kinetic energy. We didn't add any gravitational energy to the system because the track was level. So at every point, its potential energy was the same, and the gravitational force did no extra change in the motion. No extra change in the motion. So here we have our ijk axes, ijk just like x, y, and z, and we say, let me define it so that two vectors that are going along the x direction, the I hat direction, will become just simply one, and the same j dot j and k dot k. Now remember, these hats indicate the unit vector, so those are magnitudes of 1. So when we multiply this, we're getting back the magnitude of just 1. We define two vectors being multiplied in such a way that the dot product results in the cosine of the angle. And we want this to be defined in such a way that the magnitudes are multiplied and the angle between them we want to be 1, which we get when we multiply, when the angle is 0 between them. The cosine is the only one that gives us, of those sines and cosines, that's the one that gives us a 1 back. So we want the magnitudes and then 1. We also want it so that I dot j going on those two axes is 0. Cosine also meets that condition because these are 90 degrees to each other. Cosine at 90 degrees should be 0. So therefore, if we write down I dot I, therefore if we write down I hat times I hat dotted into it, so therefore the proof is if we have I dot into I, we're going the same direction, these two vector components are going the same direction, then the magnitudes of those two are going to be multiplied to each other, and the cosine of the angle between them, which is 0, gives us 1. The magnitudes of these is also 1, and we result in a scalar value 1. This is what's going on and why the force vector, the displacement vector go away, and the magnitudes of the force and the displacement are what results in a scalar work is a scalar. It doesn't matter what direction you're going. When you have a kinetic energy, you have that kinetic energy. It's not directional. It's not dependent on what direction you're going or the force that's causing your displacement. You'll have the same energy going this direction as you go this direction, using the same force and general displacement concepts. Da, 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 da. All right, I think that's everything.